Right, so I guess this is recording. So let's get started. Okay, so today we're gonna start a new chapter, which is really a power tool for structural analysis, okay? So that one is called Principle of Virtual Work. And energy principles. Okay, so we're gonna start with the principle of virtual work. This is really the main idea. And because of this, then you can move to the energy methods. But the main concept is the one of virtual work, all right? So principle of virtual work. Okay, so if you remember from dynamics, you have the Newton's equation, Newton's second law, that will be summation of forces equals to ma, okay? We can rewrite that equation as summation of forces equal to m dv dt, okay? Now, if we do the chain rule, this is equal to m times dv ds time ds dt, where here s is the position vector. So since a vector, we can put a little bar on top. So now, what is the physical mean of distance divided by time? So that is the velocity. Okay? So this is just a derivation of what is known the principle of work and energy that you do in dynamics. So over here, now this is equivalent to summation of forces equal to m v dv ds. Okay, so this is a basic differential equation. What is the general procedure to solve a differential equation is to separate the variables. All right, so what are the two variables here? Velocity and position vector. So if we move the position vector to the other side, we have summation of forces ds will be equal to m v dv. Okay, so now that we have separated the variables, what we can do is to integrate. So if you integrate the right-hand side, you end up with what? You have here summation of forces ds will be equal to what? 1/2 mv final square minus 1/2 mv initial square. Where this term over here, you know that is equal to the change in kinetic energy. Okay, but this term over here is not important. The important term for us here is what? Is this term on the right-hand side, which is what? Force times distance, which is what? Work, okay? That's why this is generally known as the principle of work and energy, or the principle of work and kinetic energy, okay? So this one is force times distance. All right? So now, we know that in structures, what is the basic equation in structure? Is summation of forces equal to 0, no? So everything we assume in structures, which is not always good, but we assume what? That the problem is static, which will involve what? That the velocity is 0, meaning that the change in kinetic energy will be equal to 0, no? Okay? So if you want at the end, we have one equation that is equivalent to summation of forces equal to 0. Our equivalent equation here will be what? Summation of forces ds will be equal to 0, no? Basically, we can say this equation is the same as this one, we just rewrote it differently. Okay? All right? All right, so over here, so this is force, this is easy. And the important thing to see here is that this is deformation. So this is important. Work force times distance or force times deformation. Okay? So the whole concept of this, and it's an extremely powerful tool, is that let us assume a deformation that we're going to call a virtual deformation. All right? So here, if we say, assuming a virtual deformation, let's say, let's call it delta S, what would that give us? We have the summation of forces integral d, but now S was the deformation, no? Now we say we're going to assume a virtual deformation. Okay? So this is exactly the same equation as the one we had before, where this is deformation, this is our virtual deformation. And this should be equal to 0. So what happens here is that since the forces are assumed to be constant, you can rewrite this as what? You can move the virtual sign outside, and what you're going to have is that you end up in the middle with the same expression that we had before. Summation of forces ds which this term is what? What is the physical meaning of this term? This is work, okay? So let's say we say this work, we call it with the letter W. So then at the end, what do we have? We're gonna have one equation here that says that partial W for work equal to 0. So this is the equation of principle of virtual work. Okay, so I know at first sight this equation looks very confusing because you say, how can this equation be a powerful equation, no? All right, we don't really see what it means right now. But basically what you need to see is that the idea behind is that in order to solve a problem, you don't know what is the deformation, but you can assume that there is a virtual deformation, and then you can see what will happen due to that virtual deformation, and you can solve then for the forces, no, causing that deformation, because you know the whole thing needs to be equal to 0. Okay, so let's do 2 quick examples. So if you want this equation here, replace from now on our equation, which is summation of forces equal to 0. It's kind of equivalent. All right, so example. Okay, so the principle of virtual work is, like I mentioned the other day, is a very powerful tool, but like powerful tools, they will make easy problems sometimes more complicated, but they will make difficult problem a lot easier, okay? So let's say if you only have a pair of pliers, yeah, you might be able to remove few little things, no? But let's say you had to change your tire in your car with a pair of pliers would be difficult. However, if you have some type of power tool, it would be a lot easier, no? But if you want to just, whatever, tied up a little screw, if you have the power tool, you're going to end up spinning the screw or something, no? Okay? So this is one of those things. It's a powerful tool, but for the simple problems, it actually makes them more difficult. But for the difficult problems, it makes them a lot easier. All right? So the first example is very, very simple. Basically, is from statics. So let's say you have a beam, I mean a bar. That will be pivoting about a point. Okay? And you know, there's a force here, P, subject that and A, and a force Q over here. All right? And that distance here is A. That distance over here is B. Okay, so very simple problem. The question here is to determine Q in function of P such that the bar is in equilibrium. So basically, if you apply a force P on this side, what should be the value of the force Q? So if A and B were equal, what would you have? Q equal to P, no? Okay, but this is the pivoting point is not at the middle. So what is the equation you need to use for this? The equation to use will be that if you want this in equilibrium, what do you need to have? Summation of moments, no? About point C needs to be equal to 0. All right, and I always select, so it's important that you always specify about which point when you take moments. If you don't put about which point, nobody can know what you're doing. All right? So this is very simple. If you do this, what are you gonna have? P times A is going counterclockwise, so that will be positive, minus Q times B, because this one will be going clockwise, equal to 0. So in this problem, they ask you to find Q in function of P. So you're gonna find Q equal to P times A over B. Okay, so you see, very simple problem. Now, this is a problem that the power tool is gonna make it a little bit more complicated. If you want to stick with that one, then I'm going to give you a problem about how to find the deformation. And you're going to see what I'm talking about. All right. So basically, we come here now and we say, let's solve the problem using virtual work. Okay? So the virtual work equation is this one over here. So I will summarize it at the end, but the whole idea over here is to assume a virtual deformation. Okay? So if I do the figure over here again, okay, well, here you're gonna have, okay, so let me first assume the deformation and then we can see how I can do the plot. So this now can move, what could happen if this could pivot this way or could pivot this way, no? Okay? So let's just say pivot counterclockwise, all right? But you can do it in the other direction. So basically you assume that it's pivoting counterclockwise. So we know this is point A, this is point B, this is point C. Okay? So we assume a deformation, so that means that it's going to be a deformation here. And be careful here with the notation, it's just notation. We're going to assume our deformation here is delta Q sub A. Okay, you could call it Y sub A, but let's call it Q sub A because that's generally the way it's called in the textbooks. And this one over here will be what? Similarly, we could say this one is delta Q sub B. All right? And I don't want to put too many things in that figure, but maybe What do we have on this end? This is the one due to the force P, and this one here is the one due to force Q, no? Supposedly, all right? Let's see what else we have. We know the distance here again. This is A, and that distance over here is B. Okay, now just a reminder is that work is force times distance. And generally the sign convention for work is that if you push, let's say, a table forward and the table is moving forward, that's positive work, no? But let's say you're going uphill and you push the table forward, but you end up going backwards, that means that the work would be negative. So if the force and the deformation are in the same direction, it's said that the work is positive. If the work and the deformation are in opposite directions, it's said that the work is negative. Okay? So using that, let's just use here the principle of virtual work. So we have principle of virtual work equal to 0. So now, what is the virtual work done by the force P? It's force times deformation. So what is the value of the force? P, the deformation is delta Q sub A, and they are going in the same direction. So that should be positive. Now, if you look at point B, what happens? The force goes in the opposite direction than the deformation. So that would mean that the work is negative. So minus Q over delta Q sub B. And this should be equal to 0. Okay? So now this becomes just math. Here we have one equation. How many unknowns do we have? 2, Q sub A and Q sub B. Can we find a relation to relate these two quantities, delta QA and delta QB? So this one is done very simply. Let's say we look at the angle over here. This angle should be the same, no? Yeah? So our second equation could be what? Tangent of theta, if we first check on the left-hand side, should be equal to what? Delta Q sub A. So sine over tangent, what would be the cosine of that place will be A, no? So height over length, and this should also be equal now on the other side, delta Q sub B over B. So this here is going to give us the relation, for example, saying that delta Q sub B will be equal to what? B over A delta Q sub A. Or you could do or you could put delta Q sub A, doesn't matter. Or we could just leave it under this form. Okay, what's important here that you notice is that the first equation will always come from the equation of virtual work, and the second equation will come from the geometry, okay, or the deformation. So keep that in mind. And this is, what type of system is this? If we think about this way, this will be like an undeterminate system that you can only solve with this one. You need to find some type of other equation, no? So it's not directly. Okay, so now what happens if we combine the two equations? So combining 1 and 2, we have the following. So we're going to have P, let me just rewrite it, delta Q sub A minus Q delta Q sub B equal to 0. Okay? Or we can just rewrite delta Q sub B using equation 2. This will be equivalent to P delta Q sub A minus Q of B over A delta Q sub A, and this is equal to 0. Now, what is a good thing is that we can factor out by the delta Q sub A, and this is going to give us P minus Q times B over A equal to 0. So I know in aerospace you don't have a class called vibration, but actually what we're going to do next is the same reasoning in order to find solutions to, if you want, dynamic equations, is that the principle of virtual work actually also works for vibration. So over here, what is the equation? They say, remember, this equation here is equivalent to this one, no? So we know this equation needs to be equal to 0. So when can that happen? So this, all right, let me go to the next page. Okay, let me rewrite very quick the same equation. All right, so we say the above equation is satisfied if, okay, that means if and only if, okay? Okay, what are the two options that can happen over here? Either the system is not moving, meaning that there is no deformation, no? In that case, this time will be 0 times all this. So this will give you 0. This one is of no interest, so it's what would be called here trivial solution. But now, when will this also be valid? When the term within brackets is equal to 0, okay? Or when P minus Q times B over A is equal to 0, okay? So in the second case, which is what? P minus Q times B over A equal to 0 will give you what? If we use that equation, this will give you what? That Q should be equal to P times A over B. which is the same thing that we found with a lot faster way to do summation of moments about point C equal to 0, no? All right? But basically, do you see the idea? The idea is that you need to assume a deformation, all right? And then once you assume the deformation, you do the calculations like if you knew it, and you apply this condition over here. When is the cases when that equation is equal to 0? Okay, we're gonna do another example. Now it's gonna get a little bit more complicated. So example. So this time the example is, if you want, this is like an idealization, but let's say you have a bar. We have a force P at the tip. And now let's say we have a spring over here. So the stiffness of the spring is K. And the distances are here. B and A. So now the question is, let me check, yeah. Determine, so hold on 1 second, I need to put some A and B. So the question here is determine the deformation at point B. So now, this problem now is where really the principle of virtual work is a lot easier than to do summation of forces equal to 0. If you remember from statics, probably, yes, statics, what would be the way to find the deformation? If you remember, you find the moment, and then you have an equation which is the second derivative of the deformation with respect to the span-wise is equal to the moment over EI. You need to integrate twice and then solve for the two constants. You might not remember, but that's the way it is, no? Okay? All right, so let's see what it would be over here. All right, so like always, I mean, this is the same thing in every single class. What is the first thing you need to do? You need to do a figure or some type of sketch, no? All right, so if you want here our free body diagram, I just write it for the first time, free body diagram. So if we have our beam over here, I'm leaving it attached over here. We know we have a force P over here. We're gonna assume a deformation, no? So we can do it up or down, but in this case, I think it's easier to just to do it Down, no? Assume deformation. Okay, we had a spring over here, no? So what would be the spring doing if we deform it down? It would be creating a force pushing up. So we'll have it here, a force now. Maybe I can put it here. A spring will be here. We know this is point A, this is point B. And again, the same as before, we did assume a deformation. Well, that deformation over here will be delta Q sub B. And this one over here will be delta Q sub A. So we have the figure. So step one, to do a figure. All right. Step two will be to apply our equation, which is what? Write the virtual work equation for the above figure. Is like statics, Fibonacci diagram, summation of forces. Dynamics, Fibonacci diagram or dynamic diagram, summation of force equals to MA. Okay, same procedure. So now, what would be the equation over here? So let's start by, which one you want to start? F spring or P? Let's start by the spring force. So we have F spring times delta Q sub A. Now, is this one positive or negative? The deformation is going down, but the force is going up, no? So this one, this term here should create a negative virtual work. And now at point B, we're gonna have plus P delta Q sub B, and this should be equal to 0. Okay? So this will be our first equation. Let's wait before putting it. Now, in this equation here, I hope you remember this. What is the force created by a spring? Is K times the distance, no? So this will be K. So you want like Kx, but here we're gonna call it K Q sub A. And there's a reason why I don't call it delta this time is because it will complicate the notation. Let's just call it Q sub A, okay? It's just notation at this point. All right, so we do that. That means that this is like the enter sign. That means that the above equation, we can rewrite it as minus K Q sub A delta Q sub A plus P delta Q sub B equal to 0. And this will be our first equation. Okay, so at this point, we found the first equation. There's two unknowns, delta Q sub A, delta Q sub B. What is the first step? Is to write additional equation using geometry or slash deformation. Deformation. So here we go to very basic trigonometry. This is our original bar. That is the form. We know this is delta Q sub B. And this is delta Q sub B. Q sub A, sorry. So using very simple trigonometry, what can you say about the tangent of the angle? Will be, oh, correct, I forgot to put those distances. So we had that distance here is A, and this one is B. So that means that we're gonna have delta Q sub A over A will be equal to delta Q sub B over the total length, which is A plus B. Okay, so now we have a relation between delta Q sub A and delta Q sub B. So let's say we write delta Q sub A equal to A divided of A plus B delta Q sub B. Let's say that would be our equation 2A. Okay, what would be the page number over here? Would be 68. All right, and similarly, so just using the same relation, which is this one here, we could say that Q sub A is equal to A over A plus B Q sub B. So the step 4 will be solve, which will be what? Combining equations 1 and 2A to B. let's see what we have. So equation 1 was minus k q sub a delta q sub a plus p delta q sub b equal to 0. Okay, so we're just going to write the same equation. So we're going to have minus k. What would be q sub a? The expression we are over here from 2b would be a divided by a plus b q sub b so this term over here is q sub a and now what would be delta q sub a? Will be the same thing, a divided by a plus b delta q sub b, so this will be delta q sub a plus p delta q sub b equal to 0. So now, if I factor out by what is now the only virtual displacement we have is delta q sub b, no? In every single term, so you can factor out by delta q sub b. And what are you gonna have? On the first term, you're gonna have a over a plus b squared times q sub b plus p. And this should be equal to 0. Okay, so this is our equation. So the same procedure as before. Did I forget the k? So, on the first equation, yes. So on the first equation, we need the k over here. We're gonna put it. Let me put it over here. Thank you. So k, and I forgot this k is over here. And actually, this should be negative. The same thing. The first time should be negative. So, okay, let me just rewrite it very quick. It will be easier than just try to crowd everything. So this should give us delta q sub b times minus k a over a plus b square q sub b plus p equal to 0. So this is equivalent to the equation we started with, virtual work, no? Delta W equal to 0. So now, as before, we need to see when is this equation satisfied. So the above equation is satisfied. Again, I put the if with the 2F, which means if and only if. What happens? Either delta Q sub B equal to 0, that basically means there is no deformation, okay? So this will be the what is known as the trivial solution. But basically what it means is that in our case, it has no physical meaning because it means there is no deformation. Or then what could happen? The term within bracket is equal to 0. So you can write, or let me put it in blue, or minus K A over A plus B square Q sub B plus P equal to 0. All right, so if we solve this second equation, all right, so solve, so now we can just take that equation, so minus K A over A plus B square Q sub B plus P equals 0. Gives that P is equal to K A over A plus B square Q sub B. But here we actually need to solve for Q sub B, which is the deformation at point B, which gives us what? P divided by K times A divided by A plus B squared. Where Q sub B is the deformation at point B. All right, so at this point, let me summarize the procedure, even though I think I did it during the process, doing both problems. So general, procedure has 4 steps. So the first step is what? To draw a figure slash free body diagram. Okay? That was the first step. draw a figure, three-body diagram, assuming or showing. It's better to write showing. I think write showing, assuming or showing the virtual deformation. That was the first step we did. Now, from the figure or the sketch, whatever you want to call it, what do? We write the equation for the virtual work. So, unless the problem is very, very simple in all the cases so far, and that will be the case, we need to find additional equations or relations. So we find let's say, geometrical deformation relations. In textbooks, generally they're called geometrical, but I like to call them really deformation relations because they come from the deformation, okay? Or from the geometry of the deformation. And step 4 will be always solve combining equations from steps 2 and 3. Okay, so now I'm just going to stop with one thing. I'm going to finish this video with just one more thing, is that okay, the modeling of having a spring. So let's say you have a real structure. That let's say that will be this bar, okay? Which is basically the problem we're doing. So this is what happens in real life. What is a way to do the idealization of this structure? Is always to simplify the structure, okay? So in this case, what do we do in this problem? But I'm going to do it here more general, is that in real life, you cannot say that a structure is 100% cantilever or one structure is 100% simply supported, because this is an ideal case, okay? So in the real life, what will be? So let's say you assume that this can pivot a certain quantity, all right? And now all the stiffness of the structure resisting the deformation, you can model it as what? You can model it as the stiffness of springs along the length, or you can just put one, no? all right? So for example, what would be the way to determine the stiffness if it was only one spring? What is the equation that is generally used? So the force that is known for the spring is what? Force equal to Kx, no? Okay, so in this case, what is F? Will be K, no? So let's say, and this is the way generally people will do it, like for real wings. Do you think people in real wings are able to know exactly what is the EI, the E, the material, yes, but the I of the structure? When they do modeling, what they do actually is that they have a wing, they place a load, generally is a hydraulic system, they press it down so they know the value of the force, and they can measure how much is the deformation, no? And they do that at multiple stages of the wing. So at each stage where they do this, they can determine the specific K for that location that will be equal to what? Force divided by deformation. Okay? So let's say if you had a wing, kind of completely make it up this, if you had the spring and let's say this was the length of the wing, so length, and maybe you have seen somewhere this figure. So what would be the stiffness bigger? Obviously it will be at the root will be the maximum value, no? But let's say you have different springs. So let's say you could have something like this, something like this, and then something like this, no? At the end, the value of the springs is not going to be zero, but should be minimum because the deformation will be large, no? Yeah? Okay, so this will be stations, okay, where the springs are, let's say. This would be just for 2 springs. So we can use the method of virtual work once the structure is idealized to calculate the deformation and what would happen in an aircraft structure. Okay, that's the whole idea over here. Okay, so this will be the end of this video.